We've been learning about impulse and momentum, and we've seen how to define both. The momentum as mass times velocity, and the impulse is the average force multiplied by the duration, or the integral of the force versus time. But now in lab, we've seen the connection between those two. We've seen that the change of an object's momentum is in fact equal to the impulse delivered to it. Now technically, the impulse has to be due to the net force, not just to a particular force. But the concept of impulse and momentum is usually applied to situations like collisions, or the example of the baseball and the bat, where you have a very violent interaction that is short-lived. And during a situation like that, the net force is, for all intents and purposes, just the force due to the collision itself. In the example of the baseball and the bat, in addition to the force exerted by the bat on the baseball is also going to experience some air resistance and a gravitational force. But during the time the baseball and bat are actually in contact, those other two forces are absolutely irrelevant. Now, they're critically important for understanding what happens from long before to long after the baseball and the bat collide. But during the collision itself, we can pretty much ignore all the forces except the one due to the collision because it's so much larger than the others. In any case, we can write this idea of change of impulse equaling momentum like this, or another even more useful way in many cases to write it is something like this, where we can think of the impulse as whatever you have to add to the initial momentum in order to get to the final momentum. And although the units are usually expressed differently, Newton seconds for impulse and kilogram meters per second for momentum, if you actually break down what a Newton is in terms of kilograms, meters, and seconds, you discover that those are actually identical. They're just usually written differently to emphasize whether you're talking about an impulse or a momentum. But certainly if you deliver an impulse of 10 Newton seconds worth of impulse, that means you're adding 10 kilogram meters per second of momentum. Now, another way we can package this concept, if you like, is to go back to the definition of impulse as the integral of the force versus time. If we undo the integral, so to speak, we can get the rate of change of momentum is just equal to the net force, which is to say dp dt is equal to the net force. So either one of these ways of thinking about an interaction can be very helpful. Now let's apply what we know about momentum and impulse to systems of particles. So the idea here is we have to choose a system, which is to say we have to choose one or more objects that we want to focus our attention on, and then we can define what's called the momentum of the system. We find the momentum of each part of the system, add those all together into one big total. And then once we've defined the system, any forces acting on the different parts of the system can be divided up into one of two categories. There are internal forces. Those are forces exerted on one part of the system by another part of the system. And as it turns out, internal forces can only rearrange momentum within the system. They can't actually change the overall momentum of the system. On the other hand, there are also external forces, forces exerted on things that are in the system by things that aren't in the system. And those forces can, in fact, transfer momentum into or out of the system. So if we apply that formula that we learned about dp dt equals the net force, if we apply that to the equation defining the momentum of the system, what we discover is this. We discover that how the momentum of the system itself changes is determined by the net external force, which we can write like this. So this is then how we can study the momentum of a system. Any changes in the momentum of the system are going to be to those net external forces.